Hi, this video is going to discuss measures of regression and prediction intervals. So in another video we discussed the linear regression line, and now we're going to be looking more closely at those deviations, the difference between that line and the actual data points. And we're going to use information to decide how much of our deviation has been explained, how much is left unexplained, and then the total amount of deviation. So the total variation around a regression line is the sum of the squares of the difference between the y value of each ordered pair and the mean of y, so the y bar. The explained variation is the sum of the squared difference between the predicted y value, y hat, and the mean of y, y bar. And the unexplained variation is the sum of the squared differences between the y value of each ordered pair and each corresponding predicted y value. So the total variation is the sum of explained and unexplained variation. So based on that, we can find what's called the coefficient of determination, and that is simply a ratio of explained to total variation. And you can imagine, based on the previous slide, what that equation will look like once we substitute explained and total for what those are mathematically. So the correlation coefficient that represents the number of hours student watched television and test scores we found was negative 0.831. Now we're going to find the coefficient of determination, and we find that about 69.1% of the variation in the test scores can be explained by variation in the hours of TV watched. About 30.9% of the variation is left unexplained. Next, we can discuss the standard error of estimate. Recall that a y value, y hat value, is predicted based on an x value, and the prediction is a point estimate. So an interval can be constructed around a point estimate, as we've shown in the past. So the standard error of estimate, SE, is the standard deviation of observed y values as they surround the predicted y hat value for a given x value. And the equation is here, where the standard error of estimate, SE, equals the square root of, in the numerator, the sum of yi, which is the observed, minus y hat, which is the predicted, squared, so the squared, sum of squared residual there. And then in the denominator, we have simply n minus 2, which is our sample size of ordered pairs in the data set. And the closer the observed y values are to the predicted value, the smaller that standard error of estimate will be. So these are the steps involved in finding the standard error of estimate. We need to first make a table that includes the column heading shown. We use the regression equation to calculate the predicted y values. We calculate the sum of the squares of the difference between each observed y value and the corresponding predicted y value. And then based on that, we can find our standard error of estimate using our equation. So here's an example of some data. The regression equation for the data is y hat equals 1.2x minus 3.8. So now we're going to find the standard error of estimate. There's our x values, there's our yi values, which are the observed values. This is our y hat predicted value based on our equation, regression equation. And then the sum of the squared difference between those yi and the y hat I values. We put that in our equation, and then we come to the value of 0.365. So the standard deviation of the predicted y value for given x value is about 0.365. We can also note that the sum of the difference between yi and our observed y and our predicted y will tell us about our unexplained variation as well when we sum that up. And here's another example. We have a regression equation for the data that represents the number of hours 12 students watched television and the test scores they got on Monday. The y hat, our predicted y value, equals minus 4.07, which is our slope, times x value. plus 93.97, our y-intercept. So if we have that, we can find our standard error of estimate. There's our test scores. There's our predicted test scores. There's the difference between the observed and predicted. And down here we've got our x's, our test score y in the next row, our y hat I, and then the sum of squared deviation. So the sum of the squared deviations is our unexplained variation, and we can use that to get our standard error of estimate with our equation. We plug that into our formula and we come to 8.11. Standard deviation of the student test scores for a specific number of hours watching TV is about 8.11. Next, we can think about prediction intervals. And we could say two variables have a bivariate normal distribution if, for any fixed value of x, the corresponding values of y are normally distributed. And for any fixed values of y, the corresponding x values are also normally distributed. So, based on that assumption, we can look at prediction intervals. We can construct them for the true value of y. So given a regression equation that we've looked at before, and a specific value of x, a C prediction interval for y is here. This is our margin of error expressed mathematically. Predicted value of y minus error less than y, which is less than the predicted value of y plus error. So how do we get E? This is our equation for that. We have our t value times our standard error of estimate times the square root of 1 plus 1 over n plus this portion, which is the sample times x sub 0 minus x bar squared. And then in the denominator, the sample times the sum of x squared minus the sum of x squared. So the point estimate is y hat, and the margin of error is E. The probability that the prediction interval contains y is C. And these are the steps for setting up our prediction interval. First, we have to identify the number of ordered pairs, which is our sample, n. We use the regression equation, and given x value, define the point estimate for y hat with degrees of freedom n minus 2. Then we find the critical value of t that corresponds to the given level of confidence using our t distribution table based on degrees of freedom. We then find our standard error of estimate, and then we find the margin of error using the t and the standard error of estimate values, as well as information about our sample and our x values. Then we find the left and right endpoints that form the interval using this equation. So we'll set up our prediction interval using our original example of the 12 students and their TV viewing and test scores. And we have our equation already here. We have our standard error also found previously as 8.11. And we're going to look at a 95% prediction interval when 4 hours of TV are watched. So we have to find our point estimate. And if we plug 4 in to our equation, we'll get our point estimate, our predicted y value indicated by y hat. And then we find our critical value of t based on 95% confidence, and our standard error of 8.11. And from that we get our lower and upper bound endpoints for our interval. So you can be 95% confident when a student watches 4 hours of TV that their test grade will fall between 69.58 and 85.8.